Hi guys, Mrs. Thompson here. I'm going to cover atoms, ions, and isotopes. Here's the basic structure of an atom. And in this table, you have what those particles are. You have negatively charged electrons here in blue. Those are outside of the nucleus in what we call the electron cloud. In terms of their mass, they are very, very tiny. They are 1,840th of the size of a proton. They are actually too small to even count. So when we figure out our mass, we're not including those electrons. All right, in the center, you have the nucleus, you have the positively charged protons, the neutrally charged neutrons. Those each have a mass of 1 atomic mass unit. And so when we figure out the mass of an atom, we simply look at the protons and the neutrons. Let's go over that nucleus. Again, it's the tiny dense center of an atom. It contains both the protons and the neutrons, and it's how we figure out the mass of an atom. The electron cloud is the region where those fast-moving electrons are traveling through empty space around the nucleus. Remember that Rutherford figured out that the atom is mostly empty space, so those electrons live out there in that mostly empty space, and they're zipping around. Now, what keeps them from flying off into space and being stuck within that atom is the fact that they are attracted to those positively charged protons within the nucleus. In terms of neutrons, they don't have a charge. They're just kind of there to buffer that positive charge. All right. There are several ways in which we can show the notation of an element. And so I've got 3 versions. We've got the periodic table version, we've got what we call the isotopic notation or symbol version, and then we have the mass notation. We'll go through each. So in the periodic table, what you'll notice is at the top, you'll have the atomic number, then you'll have the element symbol, the element name, of course, and on the very bottom, you have the average atomic mass. We'll go over that too. In the isotopic notation, it's written with the mass number at the top left, the atomic number on the bottom left, the symbol, so Mg, magnesium in this case, and then you have the charge in the upper right-hand corner. For mass notation, you simply have the element written out in its full form, its full name, and then you have the mass number. Okay. In isotopic notation is the only one where you will see a charge in there if there is a charge. If there isn't, it'll just be blank in that section. All right, we're going to go through some of those things that we just covered within those notations. So atomic number is the number of protons. Some more information about that is we've got to use the atomic number, the number of protons, to figure out which element we have. So we use the periodic table. If it has 7 protons, that means that it is atomic number 7. And I look at the periodic table, that would be nitrogen. The mass number is the number of protons and the number of neutrons within the nucleus. So it's the mass of the nucleus. It is specific to the specific isotope you are looking at that time. We'll talk about isotopes in a minute. The average atomic mass is the weighted average of all of the isotopes of that element, and it's what you see on the periodic table. We do not use the average atomic mass as mass number. They are not the same thing. Because it is not the mass number, we cannot use it to find the number of neutrons. Okay, and finally in this table, we're looking at charge. And so the charge, a charge happens when there's an imbalance of protons and electrons, excuse me. We can figure it out by taking the protons and subtracting out the electrons. That's one way to do it. But what I really want you to understand is how is the relationship between the protons and the electrons? Figure out the charge. Okay, if the protons are equal to the number of electrons, we have a net charge of 0 because all of those positive things canceled out, all of the negative things, the electrons, we get nothing in terms of charge. When we look at where there's an imbalance, if there's more protons there than there are electrons, we'll have a positive charge. And if we have less protons than we have electrons, we'll have a negative charge. That specific charge will be equal to the difference between those two. We'll do some examples on that. All right, so here's some examples where we've got some neutral atoms. We've got one written in mass notation, one written in somewhat isotopic notation, just not complete. We'll go through the first one. I went ahead and took a picture of the specific spot on the periodic table, sulfur for us right here. But if you don't have that, you would look that up, right, on a periodic table. So the atomic number of sulfur is 16. Found that from the periodic table. The mass number. I remember I am not using the mass that is on the periodic table. That's the average atomic mass. That's slightly different than what we're working with here. So what I'm going to do is I'm going to take the notation, which is sulfur-31, and use that as my mass number, because that's what that 31 is showing me, my mass number. Notice how it is different because this is a specific isotope of sulfur. This is sulfur-31. Okay, there's several versions of that sulfur. All right, so let's talk about protons. Because it's sulfur, we know that it has 16 protons. It is the protons that identifies that atom. In terms of neutrons, we have to do a short calculation for this. Neutrons, to find them, we know that protons plus neutrons gives us our mass number. So we know the mass number here. We know the number of protons. We can figure out the number of neutrons. It's kind of like saying if we know we have 16 protons and we add in a certain number of neutrons, we're going to get a mass number of 31. And so 16 plus what is 31? Or we could say 31 minus 16 is 15. All right, in terms of electrons, these are neutral examples. And so anytime you have a neutral atom, the number of protons are equal to the number of electrons. Since we have 16 protons, we have 16 electrons because we have that overall charge of 0. Okay, so it's probably helpful to go through the overall charge before you figure out the electrons. Let's try that next time. All right, for this next element, we have somewhat of an isotopic notation. We have the mass number in the upper left-hand corner, and you will see that happen. What I want you to do is complete that isotopic notation by putting the atomic number on the bottom left. So this would be an 8 here, because I had to look up oxygen. Oxygen's on the right-hand side of the screen here. The atomic number then is 8. The mass number is the 17 that's given in the top left-hand corner. For protons, that's equal to the atomic number 8. For neutrons, okay, we could say 8 plus what number is going to give me that 17? So 8 plus 9 gives me 17. So we have 9 neutrons. Another nice thing about having this isotopic notation is when I figure out the number of neutrons, I'm just taking this mass number and I'm subtracting out the number of protons. So I could just say it's this minus this, that gives me 9 neutrons. All right, how about electrons? Well, let's look at the overall charge. There isn't anything in the upper right-hand corner, so we're going to assume that that overall charge is 0, or else we'd have a charge in the corner. The number of electrons then have to be equal to the number of protons. So that's also 8. All right. What happens when the number of protons are not equal to the number of electrons? You get what we call an ion. So an ion is an atom or a group of atoms, which we'll learn about later, that has a positive or a negative charge. It has an imbalance of charge. We have cations, which are positively charged. That's why you see this cute little picture that says cations are positive. Okay, that's one way to remember that cations are the positive ones. In order to become positive, they have to lose electrons. Anions are negative, and they are negative because they have gained electrons, because now they have more of what makes them negative. We don't change the number of protons when we're looking at atoms, because as soon as you do that, we're looking at a different type of atom. So it's always about changing electrons to form those ions. Okay, so let's do some examples where we're dealing with ions. The first one, we have fluorine. We have the incomplete isotopic notation, so I'm going to find the atomic number and put it the bottom left. All right, so the atomic number is 9. Mass number is given. It's 19. Protons equal to the atomic number, so 9. Neutrons. Now again, I'm just going to take my mass number, subtract out the number of protons, so 19 minus 9 gives me 10 neutrons. This time we're going to have to figure out electrons. Let's go to overall charge. So the overall charge of this is a negative. We're going to say, because it doesn't have a number, that's just -1. So you can either write the negative in the front or the negative in the back. I prefer it like this. So it's got a 1 minus charge. Okay, so in terms of electrons, we know that the protons are usually equal to the electrons. So if I was dealing with a neutral atom, this would have 9 electrons, the same as the protons. But this has got a -1 charge. That means that it gained 1 electron. So instead of saying I've got 9 electrons, I'm going to change that to 10. I've gained 1 negative thing in order to make it negative. Okay. The next one, we've got the isotopic notations complete. We know the atomic number is 20. It's the bottom left number. We know the mass number is 41. It's the top left number. We know that the protons are equal to the atomic number. We know to find the neutrons, we take the mass number, we subtract out the number of protons, or the atomic number, and that's 21. For the number of electrons, we have to look at the overall charge. The overall charge is in the upper right-hand corner in this notation. It's the 2 plus. So what we're going to say is we're going to say normally this would have the same number of electrons as it has protons. So normally it would have 20. But we have a positive 2 charge. So what does that mean? That means we have lost 2 electrons in order to become positive. I know some students think of it this way about losing weight and gaining weight. Gaining weight is a negative thing usually when we're trying to lose weight. So when we gain a negative electron or we gain an electron, it becomes negative. When we lose an electron, that's a good thing, like losing weight, and so it become positive. That's just one way to think of it. All right, so instead of 20, because we have lost 2 electrons, we're going to say that this is 18. So 20 minus those 2 electrons that we've lost. All right, you'll do some examples with those later. All right, so here I've got a periodic table of isotopes. So let's talk about isotopes. There are many different versions of some elements. Some elements have 2, some elements have 4, some elements have 5 different versions of that same element. So here's a periodic table showing those different versions in a little pie chart format. Here's the zoomed in version of that. So you can see cobalt, there's only one version of cobalt, but if you look at iron, there's iron 56, there's iron 54, iron 57, iron 58, okay, all different variations, all different isotopes. So let's talk about that. Isotope is a version of an atom, whichever specific one you're looking at. We usually talk about isotopes when we're pairing them up and saying, these two are a pair of isotopes. We say they're an isotope of each other. So here this says, when 2 or more atoms are different versions of the same element, so it's key that we're talking about the same element here, we say they are isotopes of each other. How do we know that they're different versions of that same element? We would know that because they'd have the same number of protons, indicating they're the same element, but they would have different neutrons, different numbers of those neutrons. And what ends up happening is because they have different neutrons, they also have different mass numbers. So you see 3 isotopes at the top of hydrogen. Those are all hydrogen, but they have different mass numbers at the top because they each have a different number of neutrons. That first one has no neutrons. The second one has 1. The third one has 2. So 3 different versions of the same atom. So they're isotopes. Okay, let's take a look at this last example. Here I've got a table just showing protons, neutrons, and electrons, and I want to identify which ones are isotopes in this table. So I am looking for 2 atoms that are the same element, but they have different numbers of neutrons. So if I look, this one has 4 protons, 5 neutrons. I don't even care about the electrons. Let's just look at the protons and neutrons. This one has 5 protons, so it's not the same element as this one. This one has 4 protons. It is the same element as this one. Okay. Does it have different numbers of neutrons? Well, this one has 5 and this one has 4. So those are 2 different versions of the same element. Those are considered isotopes. All right, let's double check on the other ones because I see we have one with 5 protons, so those are the same elements, but are they isotopes of each other? This one has 5 neutrons, that one has 5 neutrons, so they are not isotopes of each other. They are different in terms of electrons, so it just means that we have the same variation or the same version of the atom, but one of them is an ion. Okay, all right, that wraps up this lesson.